Hi again. So in this session, I want to solve another example to find the drag force that is exerted on this plate by the fluid. And I'm going to use all the things like the momentum and mass conservation equation in integral form to be able to find a set of equations to estimate the drag force based on the velocity of the incoming flow here. Okay, so here we have in velocity of ue, say, and here is the same thing, and the question asks us to find the drag force exerted on the plate by the fluid. Okay, so this is a question. So here we have, say, this plate here, and then we have like it could be wind or it could be water, anything that is going over that, and then it exerts some drag force on the fluid and brings the velocity at the surface of that to zero, right? So this is what we call no slip condition, right? If you just remember that, this is no slip condition where the velocity at the surface becomes zero. And here we have the leading edge. So this part of the plate, we call this as the leading edge. This plate could be anything. This could be even like a airplane wing or anything. So this is just a general approach that we are going to take. And here, this height is h, so I'm going to show it with h. And so here the velocity is kind of decreased up to here, this point. So the velocity, or u, is a function of the direction of the vertical direction. Okay, so another assumption we have is that the flow is a steady laminar boundary layer flow. This means that Reynolds number, so here I can just show the directions, so the coordinate system. So let's say we have here this is x direction, and say this is y direction. So let me just write them down. This is x and this is y. So the Reynolds number in the x direction is gonna be rho, which is density ue times x from the center, the leading edge, over mu. If you define the Reynolds number in the x direction as this, where mu is viscosity, then for a laminar boundary layer flow, it means that this should be smaller than 100,000. So the velocity is not that large, and so the flow becomes laminar. If the velocity is too large, then the velocity is not like this. It could be turbulent. So we could have something like this, okay? So these are the assumptions, and now we want to find what is the exerted force on the plate by the fluid. So in order to solve this, let's get started. So answer. First, we consider a CV extending a distance L from the leading edge. So the CV that I'm gonna consider here is this. So I want to calculate the drag force, so it kind of has to be close to the plate. And then I'm going up here. Continue. Okay, so this is the CV, and it's extended to a distance of L. So this distance is L. Okay, so this is the CV that I consider, and so this has 3 parts. I just named them. So this is section 1, this is section 2, this is section 3, and this part we have the viscosity force that we are looking for, the drag force or viscosity force, right? This is the unknown that we want to find. And here velocity as a function of y in the y direction, right? So it's not exactly ue like this part. It becomes ue far from the surface, like here, okay? So let me write it here. Okay. So if you consider that, then in order to you can see how the flow progresses over this leading edge, right? So at the beginning, so you have the full profile of UE, okay? But then as the flow goes a little bit here, the no slip condition kicks in, so the velocity at the surface becomes 0, but then it doesn't see the farther locations do not immediately see the effect of the no slip condition. So it starts to diverge and then becomes UE again. And then as we go further and further in the x direction, the higher elevations feel the effect of no surface. no slip condition, that meaning that there is something at the surface, right? So they will fill it after longer distances from the leading edge. Okay, so based on this we can define something. And so here these red lines show the velocity streamline. So if you say here we have this velocity, then it's gonna go something like this, right? This is gonna be always UE. And here if say you have a velocity, so let me show it with another color. A velocity UE, and you want to show its streamline, it will go something like this. Okay. And then so these will be the streamlines of the velocity. And based on these, we can define a delta, right? So here the velocity is going to be at this point is still UE. And here is also UE. Okay. And then below this point, we have the velocity that is kind of decreasing to 0. Okay. So based on this, we define this height, which we call it delta. Which is the height for which the velocity becomes equal to the free flow or free atmosphere or free flow condition, which is UE. Okay. So one thing that you can see here is that this is also, we call this delta as the thickness of the boundary layer. And so you can see that the boundary layer, as we go further in the x direction, grows. So here the height of the boundary layer is this much. And then here it's like up like this much. And then here it kind of grows. So as we go further and further, this boundary layer height grows. So this is what we call also delta. So here I'm going to show this delta based on the definition we had. So here is still the UE is, the velocity is UE here, and then it starts decreasing, say, from this point, okay? So based on that, I'm going to define this part as gonna be delta, which is the boundary layer depth, where the velocity decreases to the no slip condition, to the 0 no slip condition at the bottom. Okay. So here we can make an assumption in order to kind of neglect the pressure differences and pressure forces. So here what you see is that the velocity streamlines and these are the streamlines that I have shown. So these red vectors here. These velocity streamlines are almost parallel. And because these velocity streamlines are almost parallel, if you have a parallel velocities like this, we can assume that the pressure differences are small. Meaning that partial P over partial Y is small. Meaning, so because the velocities are kind of parallel, so they are not changing. So we can assume this. And also in the x, that's the same thing. So also UE is constant, so U is not changing, right? So because UE is always here, we have assumed is steady flow, is not changing. So also we can say that the pressure gradient in the x direction is also very small. We don't have that much variation in the pressure also in the x direction. And because the velocity streamlines are almost parallel, we don't have that much pressure gradients in the y direction. So you see that the pressure, we can say the pressure is not changing that much here. The pressure gradient is not changing. So this flow, if we call this zero pressure gradient flow, meaning that the velocity is not changing that much. The pressure is not changing that much, okay? Another thing is at y equals to delta, which is, we call this boundary layer thickness. We define this delta as where the velocity uy becomes 99% of UE. So we don't define it exactly as where it is UE, but it's like about 99% of UE. Okay. So this is just a definition for the boundary layer thickness. So now that we have all these things, we can start writing the momentum and mass conservation. So I did this this assumption for zero pressure gradient boundary layer flow to kind of assume that the pressure is small, so I can just neglect that in my calculations. Okay, first is writing conservation of mass equation in integral form. So this is a steady flow, right? So because this is a steady flow, I can just go ahead and use this formula. So because it's a steady, so I can just neglect this part, right? It's just zero in steady flow. So I only have this part. Okay, so now let's calculate it. So first we have, I just write it here, then I will bring it down. So for the first part, we have minus UE because it's going into the control volume, so the sign should be negative. So minus rho UE, and then we have to multiply it by the volume. So it's going to be H, and then we can assume a width of W. Okay, so this is the area. And so this is going to be the mass that goes in. And then here we'll have two parts. One part that is varying, so the velocity is varying up to delta, and then the other part that is not varying. It's kind of constant, okay? And also another thing that we need to think of is here you see that, right? So you have somehow you also have some velocities that are going up. So it's feasible that we might have some we might need to have some velocities that are going up. So this velocity vector that is here, this streamline, has one component in the x direction and one component in the v direction, right? So I also need to write the velocity, the vertical velocity that might go here, that might go out here. So it could be small. It's smaller than the other parts, but I also need to write it down in the mass conservation, because this is also going out of the considered CV in order to be accurate. Okay, so let me see. Let me see if I can bring this down here so we can see this better. Okay. Okay. So here is x direction and here is give me a second. So here is, yeah, x direction, here is y direction. So I'm going to write it for all the sections that we have. And assume that the width of this plate is also W. So the plate could be something like this. And so the width is W, okay? So here we have section 1. And here this is delta. And what else? So section 2 and 3. Okay. So first let's go, we wrote it for the section 1, which is going to be minus rho UE H times W, where W is width. So this is going to be the area. And so the whole thing is mass flow into the CV. And then I want to calculate the mass that goes out of that. So I have rho. The density is constant here, so I can take it out of the integral. The first thing I have is up to here, up to delta, we have U. The whole thing we have Uy. Okay, so let me just write it down generally. So 0 to h of Uy W dy plus, also we have the, again, as I said, the velocity that goes out here. So I need to account for that. So it's going to be rho 0. Now we have 0 to L, because we have to integrate over here, 0 to L of Vx, because the velocity here is V, we can write it as Vx. It can vary in x direction. Vx W dx. And this is the mass that goes out from the top of the CV, and the whole thing equals to 0. Okay. And here I can do this integral, decompose it into two parts. One is the integral from 0 to delta of uy w dy, and then the integral from delta to h, and the velocity from delta to h becomes ue from here, right? So ue w dy. And so here, this is going to be just ue, because u is constant, I can take it out of the integral. And w is also constant, I can take it out, uew. And it's just going to be h minus delta. Okay, so this is going to simplify our equations. Why? Because here we have also hw, so this is gonna, the delta part, the h part, h minus delta part is gonna be canceled out. So what I'm left with is minus rho ue so the UEWH is going to cancel out, and I'm going to only have UEW delta minus UEW delta, or delta W, plus the integral from 0 to delta UY W dy, plus rho, the integral from 0 to L Vx W dx equals to 0. And so W's are going to also cancel out, so I can just write it like this. Or let me do it like this. It's going to cancel out. So we are left with one equation for mass conservation. Okay. So the second thing I need to write in order to get the drag force is momentum conservation. So the momentum conservation equation, let's you have it here. So for a steady flow, again, this part is going to be 0, so I'm not going to write it down. So I'm just going to write these parts. So let's first write that part. So this is momentum conservation. This equals to sum of the forces. Okay. So the first thing is here we have velocity, the momentum that goes into the CV. So it is rho minus, because it's going in, so I'm just going to write it a negative sign, minus rho UE, okay, times UE HW, and it's in the x direction, so I'm just going to add a I, because we have two directions here. Momentum, for the momentum equation, is a vector, because this is gonna, the this is going to be a vector, right? So I need to have a direction here, unlike the other one, because this one is not going to be a vector. Why I write it W here? Sorry, this is not W. This is row V. And then here, I think I have a small typo. Let me see, where was it? Yeah, there is no D here. Just make sure everything is correct. Yep. There is no D here. This was a typo. Yeah, so this term is not a vector, because what we are doing here is we are actually multiplying a dot product of two vectors, which is going to be a scalar. But here, this is a scalar and this is vector, so the product will be a vector. So I need to have a vector sign here. It's in the I direction. And then the second thing is the velocity, momentum that goes out here. So I can just write it down. So I have rho, which is constant. I can take it out of the integral. So I'm going to do it for two parts again, like the previous one. First, 0 to delta of uy in the I direction times w dy. So this is going to be the area. And then the second part is 0 rho delta from delta to h, where ue is going to be constant here, right? So it's just ue, the velocity is just ue. So ue square w dy. And then plus, the other thing I have is for this part, for section 3, I also need to write it down. So this is going out. So I have, this one is, you need to be careful. So we have 0 to L, okay? So the first one is n dot rho v. So what is going to be n dot rho v? N here is up. So for the velocity component, the one that is going there is going to be just the Vx, right? So this one that we calculated. So it will be, the first component is Vx, okay? But how about the second component? The second component is the total velocity component. So this was Vx. But how about the second one? The second one is the total velocity component. So it's going to be 0 to L. So here, the velocity is ue, right? Based on what we considered here. So it's going to be ue in the I direction and Vx in the j direction. So this is the total velocity vector. Okay, this is the total velocity vector that is coming from here. So this is what I'm writing here. Okay, and this just Vx. Okay, and then multiplied by Wx. Dx equals to sum of the forces. So just one thing here, I can, because this is all constant, I can take this out. So this is going to be rho ue square W, these are all constant. I can take them out of the integral, factor them, and then this is going to be h minus delta, and this is in the I direction. So I forgot an I here, I. So the whole thing is in the I direction, right? This is just this part that I've written. Okay. So let's see what are the sum of the forces. So the sum of the forces here is first the pressure gradient difference forces. Then we have the weight of the fluid. Then we have the external forces, so we don't have any external forces on this. And then the next thing we have is two forces. First one is the viscous forces that act in the negative direction with respect to x. And then we also have something we call lift. We might have also lift forces that's kind of pushing this up a little bit. So we have minus F viscosity in the I direction and plus FL J. Okay. Again, because so here the external forces is 0. The F delta P, we assumed it's 0, right? Because we assumed that this is 0 pressure gradient flow. That is because the velocity streamlines are almost parallel with each other, and U is constant in x. And this one weight is, we can also consider is it's 0 because air, we can assume it's the airflow, so its air is light. So we can just assume this one is also 0. So we are only left with F viscosity and F lift. So I'm going to write the x component of the momentum equation. And the reason is we have what we want in the x direction, which is F viscosity. So if we write the x component of the momentum equation, so we have here, the first term is minus rho UE square. And then these two terms again are going to cancel out. So this h is going to cancel out with this h. So let me write it here. So this h is going to cancel out with this h. So we are only left with this delta here. So we have minus rho UE square delta W plus the second one is here. So it's rho W 0 to delta uy square dy and then the third term is this term in the x direction. So we have plus rho 0 to L, the integral over 0 to L of Vx UE W dx, and the whole thing equals to minus F viscosity. Okay. Okay. So now I want to use this mass conservation equation. So now use mass continuity. Let's clean here. So the terms that I have here are this. So I want to write something based on Vx W dx to get rid of this term, or have a substitution for this term, because I don't know what is Vx W dx. So I have it here from the momentum, from the continuity equation. So I have integral of Vx W dx 0 to L equals to what? From here you can say that, right? So it equals to UE delta W minus this term. Okay. So it equals to UE delta W minus this term, which is the integral of from 0 to delta of Uy W dy. So the integral from 0 to delta Uy W dy. Okay, so this is what we have from the mass conservation. So now we multiply it by UE, and what we get is this. So it's 0 to L Vx, U is constant, I can take it into the integral, U is square delta W minus 0 to delta Uy UE W dy. Okay. So first, this equation is our equation 1, and this equation is equation 2. So substitute 2 in 1, and what we get is this, minus rho integral from 0 to delta. So these two terms are going to cancel out. So here we have a rho. So let me just also write a rho. So these two terms are first going to cancel out, right? And we are only left with these terms, this term and this term. So minus rho times 0 to delta of U UE Uy W dy plus rho W, the integral from 0 to delta of Uy square dy equals to minus F viscosity. Okay. Now divide this by rho UE square W. So rho is everything is gonna go to the right. So let's see what we have now. We are gonna have 0 to delta of U over UE plus let me see what I did here. So yes, this is minus F viscosity. So what I'm gonna do, I'm also gonna multiply it by minus dy minus the integral from 0 to delta of the second term, which is gonna be U over UE square dy equals to F viscosity. This is what I want to find, okay? F viscosity is what I want to find over, sorry, we have also something here because we need to divide this. F viscosity over rho UE square W. So now we define a new variable dy over delta, and delta is constant, so it just equals to 1 over delta of dy. So instead of dy, I just want to write it in terms of y over delta, okay, for the integrals. So if you change this variable, so change of variable, from dy to dy over delta in the integral, so you're going to have this, so u over ue, the first one is just 1, and then for the second integral I can just write it as u over ue again here, and then here we have dy over delta instead of dy. And so because you have dy over delta, okay, so we need to have multiply this by delta, right? So we need to multiply this by delta to get dy, right? And now when y is from 0 to delta, y goes from 0 to delta, y over delta goes from 0 to 1, okay? So here I just write it from 0 to 1. This equals to F viscosity over rho u square W. And I just bring the delta over here, and I'm left with this equation. Have a relation for F viscosity. So this is what we call drag coefficient. It's a non-dimensional number, so we call it drag coefficient. And this one, we call it theta over delta, where theta is momentum thickness. Okay. So we have many unknowns here in the problem. Like we have u, you don't know F viscosity, and So we still cannot really solve this problem. We don't know even delta. We don't know delta, but delta is where u over ux is uy over ue is around 99 percentile. Okay, so I want to add another equation. So we have three unknowns here: F viscosity, uy, and delta. So I want to add another equation to kind of be able to solve this. So we have three unknowns and we only have one equation, because we also used the momentum, mass conservation. We just inserted it into momentum equation, right? So we use whatever we had, and we can, but I want to add one more equation, and the one equation I'm going to add is based on the Newtonian fluid assumption. So we can write another equation based on Newtonian fluid assumption. Okay, so let's see what it is. So here, say we have a boundary layer flow in a surface So I can say what is the, based on Newtonian fluid assumption, I can calculate the stress at the wall. So the wall exerts some stress, and the fluid also exerts some stress on the wall. And so based on the Newtonian fluid assumption, this stress, or tau wall, is viscosity mu times, if this is uy, du partial u over partial y at the wall. This is the relation based on the Newtonian fluid assumption, right? And what is partial u partial y? Is just the slope of the wall here. So it's partial u over partial y at the wall. This is slope. If you multiply it by the viscosity mu, you will get the stress at the wall. Okay? This is the Newtonian fluid assumption. There is a linear relation between strain rate, partial u over partial y, and stress, tau wall. So based on this, I can write that F viscosity, if we have this say we have this wall, or this plate here, okay, so at each point we have these small tau walls, right? So in order to get the total F viscosity, I can just integrate all these small elements over L. So 0 to L of tau w, which is a function of x, And then we need to multiply it by, so this is stress, we need to multiply it by this W, because it's also here, is everywhere in the flow. And then also this dx, so because these are all for these small dx's, right? So we need to multiply it by area to get the force. Okay. So now we can differentiate this with respect to x. And what we get is this, dF viscosity over dx. And if you integrate this over with x, it's just a definition of integral. It's going to be W tau wall x. Instead of tau wall, I'm going to write this. So I have another relation. So this is my equation 1. And this is going to be equation 2. F viscosity over dx equals to W mu partial u over partial y at the wall. So this is going to be equation 2. Okay. So now we have two equations, 1 and 2, but three unknowns. Which are what? Which are F viscosity, Uy, and delta. So these are the things we don't know. So we still need one more equation, but we don't have it. So to close the equations and find F viscosity, we need to know or guess the shape So in order to know the viscosity, we need to know or guess the shape of the velocity profile. From what? From like experiments. The shape of the velocity profile Uy from experiments. So this is how we typically close these equations. We typically guess or fit something from experiments to find a relation for Uy. Okay. And then once you have that, then you can close these sets of equations. Okay. Like one, you have one, relation 1 and relation 2, and you can close this set of equations. So, for example, there are many estimations for this kind of velocity profiles when you have a plate like this. So it really also depends on the plate itself, because the plate can have different shapes. Then this velocity profile is going to be different. It also depends on the roughness of the plate. So It's a very complex problem, but one estimation is for, we call this parabolic estimation. I just write it down for you if you are interested. So in this estimation, u y over ue is estimated to be as a function 2y over delta minus y over delta square. So if you have now this estimation, you can just plug it back into the equations that we have, right? So we have one equation here, and then we are going to only have delta and viscosity as the unknown, and also you can have it here, you can put it here, so you will have two equations and two unknowns, so you can close this set of equations by this estimation. Okay, so I'm not going to go through that. Let me just briefly review what we did here today. So first of all, we solved an example for finding the force that this duct acts and exerts on the fluid by using continuity and momentum equation. And then we wanted to find the drag force that is exerted on the plate by the fluid. So we draw this control volume, and then by assuming that it's a zero pressure gradient, we started writing the mass conservation and momentum conservation. So momentum conservation, we wrote it also for the x component of that, and then we substitute the mass conservation into the momentum conservation in the x direction. And we found an equation which we simplified by changing the variables into this equation. But we still need more equations because we have three unknowns: F viscosity, delta, and uy. So we also use the Newtonian fluid assumption of this problem. And so we got this equation, but we still need one more equation because we have three unknowns to close this set of equation in order to be able to find F viscosity. So we need to guess or find the shape of the velocity profile from experiments, and this is one estimation that I showed you from some experiments that have been done over plates. Okay, so in the next lecture, I'm going to drive the momentum and continuity equation in differential form using the divergence or Gauss's theorem. Thank you very much, everyone.